In the summer of 2023, a team of astronomers led by Ivo Labi published a paper that made cosmologists visibly uncomfortable. They had used the James Webb Space Telescope to look at a patch of sky and found 6 galaxies that should not exist. Not faint smudges, not ambiguous blobs. 6 galaxies so massive, so mature, that some of them appeared to contain as much stellar mass as our own Milky Way, sitting there at a point in cosmic history just 600 million years after the Big Bang. According to the standard model of how the universe grows, there had not been nearly enough time for that much matter to collapse into stars. James Webb was built to confirm the story we already believed about the early universe. Instead, with almost every new image, it keeps quietly taking that story apart. If a channel like this one is useful to you, hitting subscribe means you will not miss the next deep dive when new James Webb data comes in. Because this story is still unfolding in real time, with new papers landing almost every month that either deepen the mystery or offer a piece of the explanation. We are going to walk through exactly what Webb found, why it broke the models scientists were using, and what it might mean for one of the biggest questions in astronomy: how early the universe was actually capable of building the kind of worlds that could support life. To understand why 6 galaxies caused this much panic in the astrophysics community, you need to understand what James Webb was actually designed to do. Its predecessor, the Hubble Space Telescope, could see galaxies from the early universe, but only faintly, and only the brightest, closest examples. Webb was built with a different goal entirely. Its mirror is over 6 times larger in collecting area, and it observes primarily in infrared light, which matters because light from the most distant galaxies gets stretched, or redshifted, as the universe expands during the billions of years it travels toward us. That stretching pushes visible light out into the infrared spectrum. Webb was engineered specifically to catch that stretched light, to look further back in time than any instrument before it, closer to the very beginning than any observatory humanity had ever managed to see before it. The plan going in was straightforward. Astronomers had a well-tested model of galaxy formation, built on decades of observation and simulation, called the Standard Cosmological Model, often shortened to Lambda CDM. It describes how dark matter forms a scaffold of gravitational wells shortly after the Big Bang, how ordinary matter, mostly hydrogen and helium, falls into those wells, and how that gas slowly, over hundreds of millions of years, collapses into the first stars and the first galaxies. The model makes specific predictions about how big galaxies should be at any given point in cosmic history. Webb's first job was simply to confirm those predictions with better data than anyone had ever collected. Instead, within months of its first images going public, it was breaking them. The LABA discovery came out of the SEERS survey, the Cosmic Evolution Early Release Science Program, one of Webb's first major deep sky projects. The team was looking through the data for red objects, because in this kind of astronomy, red usually means either very dusty, very old, or very far away, and often some combination of all three. What they found were 6 candidates sitting at redshifts between 7 and 9, meaning we are seeing light that left them somewhere between 500 and 700 million years after the beginning of the universe. Based on their brightness and their color, the team calculated stellar masses for these objects, and the numbers were genuinely staggering. Some of the estimates put stellar mass as high as 100 billion times the mass of our Sun, which is roughly comparable to the entire Milky Way, a galaxy that took over 13 billion years to build. Here is why that number caused actual alarm rather than just curiosity. Cosmologists can calculate an upper limit on how much stellar mass the universe is even capable of producing by a given point in time, based on how much ordinary matter existed and how efficiently gas can turn into stars. It is sometimes called the baryon budget. When the team compared their 6 candidate galaxies against that limit, several of them appeared to violate it. Not by a small margin either. Some of the galaxies seemed to require converting gas into stars at close to 100% efficiency, when real galaxies, even the most productive starburst regions we know of, typically manage somewhere around 30% at best. It was as if someone had audited a business and found it had somehow generated more revenue than the entire economy could have produced. Science, to its credit, moved fast after that. Skepticism is supposed to be the immune system of astronomy, and it kicked in almost immediately. The original LABA measurements were based on photometry, meaning brightness measured through different colored filters, which lets you estimate distance and mass, but with real uncertainty attached. The follow-up work needed actual spectroscopy, breaking the light apart into detailed wavelength fingerprints that can pin down redshift and composition far more precisely. Over the following year, teams pointed Webb's spectrographs at several of these objects. Some of the most extreme mass estimates did come down. A couple of the candidates turned out to be lower redshift interlopers, meaning they were not nearly as ancient as first thought. and their masses shrank into something the models could actually accommodate. That is exactly how science is supposed to work, and it is worth saying clearly because a lot of headlines skipped that part. But here is the detail that keeps this story alive instead of closing it. Even after the most aggressive corrections, even after ruling out the interlopers and the measurement errors, a stubborn handful of these overmassive early galaxies held up. Spectroscopically confirmed redshifts, confirmed distances, confirmed masses that still sit uncomfortably close to, or in some cases past, the theoretical ceiling. The panic settled down. The mystery did not go away. Then Webb found something even harder to explain, and this one has a name that has become almost famous in astronomy circles, GNZ11. This galaxy was actually first spotted by Hubble years earlier, sitting at redshift 10.6, putting it at just around 430 million years after the Big Bang. Webb turned its spectrograph on it and confirmed the distance with extraordinary precision, and in doing so, revealed something strange in its chemistry. GNZ11 shows an unusually high ratio of nitrogen to oxygen for a galaxy that young. In the normal timeline of stellar evolution, oxygen gets produced quickly by massive short-lived stars, while nitrogen typically takes longer, building up gradually as an older population of stars evolves and enriches its surroundings. Finding nitrogen enrichment this early is a bit like finding a fully aged wine in a cellar that was built last week. Astronomers have proposed a few explanations, and none of them are entirely comfortable. One possibility is that GNZ11 hosted an unusually dense population of massive, fast-burning stars, sometimes called Wolf-Rayet stars, that could produce nitrogen far more quickly than typical stellar populations. Another possibility, and this is the one that gets more attention, is that GNZ11 is not just a young galaxy, but a young galaxy actively feeding a growing supermassive black hole at its center, an active galactic nucleus, whose intense radiation and outflows could be enriching the surrounding gas in unusual ways on a much faster timescale than normal star formation. A third idea treats GNZ11 as a possible early globular cluster progenitor, a dense, compact system where chemical enrichment simply runs on a different clock than it does in a sprawling galaxy. Whichever explanation turns out to be correct, the underlying problem stays the same. Something in this galaxy grew up faster than the standard chemical clock says it should have. If GNZ11 pushed the boundary, the next discovery moved it even further. In 2024, a team analyzing Webb's JD's survey, the JWST Advanced Deep Extragalactic Survey, confirmed the most distant galaxy ever spectroscopically measured, cataloged as JADE's GS Z14-0, sitting at redshift 14.32. That translates to roughly 290 million years after the Big Bang, deep enough into cosmic infancy that the universe itself was barely old enough to have finished forming its first generation of stars. And this galaxy was not faint. It was unexpectedly, almost defiantly bright. Bright enough that some astronomers described it as looking more like a galaxy from a much later cosmic epoch that had somehow been transplanted into the wrong era. The brightness matters because luminosity at these distances is tied directly to how much star formation is happening, and how much mass has already accumulated. A galaxy this bright, this early, again strains the baryon budget the same way the original Sears candidates did, except now the timeline is even tighter. There is less than 300 million years of cosmic history available for something like JD's GS Z14-0 to assemble its stars, form its structure, and light up this intensely. Every additional record-breaking discovery does not resolve the earlier tension. It compounds it. While one group of researchers was chasing overmassive, overbright galaxies, another group was quietly uncovering a completely different kind of problem. This one about shape rather than mass. Under the older model of galaxy formation, the earliest galaxies were expected to look chaotic, clumpy, irregular. The universe at that stage was violent, full of mergers and collisions, gas falling in from every direction with no time to settle into anything orderly. What Webb actually found in survey after survey was disks, rotating, relatively organized spiral and disc-shaped galaxies, showing up at redshifts where the models predicted nothing but disorganized blobs. A team working with Sears data, led by Leonardo Ferreira, analyzed the detailed shapes of galaxies going back to some of the earliest epochs Webb could resolve, and found that a majority of galaxies at these extreme distances displayed disk-like morphology, rather than the expected irregular structure. That result surprised almost everyone in the field. Disks are supposed to be a sign of a settled, dynamically calm system, something that takes time to build after the initial chaos of formation quiets down. Finding that structure this early suggests either that galaxies settle into order far faster than anyone assumed, or that our understanding of how turbulent the early universe actually was needs a serious rework. And it was not just about galaxies that formed too fast. Webb also started finding galaxies that had already finished, galaxies that had lived their entire productive lives and shut down, at a point in cosmic history when they should barely have gotten started. In 2023, a team led by Adam Carnal published a study identifying a surprisingly large population of massive, quiescent galaxies, meaning galaxies that had essentially stopped forming new stars, at redshifts between 3 and 4 corresponding to roughly 1.5 to 2 billion years after the Big Bang. The surprise was not that quiescent galaxies existed that early, it was how many of them there were. Carnal's team found roughly 7 times more massive dead galaxies than the standard models predicted for that epoch. Think about what that actually requires. For a galaxy to be quiescent, it first has to build an enormous amount of stellar mass very quickly. Then something has to shut off star formation entirely, whether through feedback from a central black hole blasting away the remaining gas, or through some other quenching mechanism, and all of that has to happen within a window of cosmic time that the models say is barely long enough for the initial star formation phase alone. It is the equivalent of finding a retired executive who somehow built an entire career, made their fortune and left the workforce, all before what should have been their first day on the job. Since Carnal's paper, at least one even more extreme case has been reported. A massive quenched galaxy identified at redshift beyond 7, meaning it had already lived and died before the universe was even 700 million years old. Step back and look at what all of this adds up to together. Galaxies too massive for the available time. A galaxy chemically enriched faster than stellar evolution should allow. The most distant confirmed galaxy ever found, burning brighter than it has any right to. Disk-shaped structure showing up in an era that was supposed to be pure chaos. And a population of galaxies that managed to form, mature, and shut down all within a fraction of the timeline the standard model allows. Individually, any one of these findings might have been dismissed as measurement error or an unusual outlier. Together, spread across multiple independent surveys, multiple research teams, and multiple completely different methods of measurement, they form a pattern that is becoming very hard to explain away. This tension does not exist in isolation either. It sits alongside another long-running problem in cosmology called the Hubble tension, a persistent disagreement between two different ways of measuring how fast the universe is expanding today. One method, based on the leftover radiation from the Big Bang known as the cosmic microwave background, gives one expansion rate. Another method, based on measuring distances to nearby stars and galaxies directly, consistently gives a different, faster rate. For years, some scientists hoped this discrepancy might come down to a systematic error, somewhere in the distance measurements. In 2023, a team led by Adam Rees used Webb specifically to check those measurements using an independent method, red giant stars instead of the usual Cepheid variable stars. Webb confirmed the original distances. The disagreement did not go away. It held up under an entirely different, more precise instrument, 2 separate cracks in the standard cosmological picture, appearing from 2 completely different directions at almost exactly the same time. So what is actually going on? There is no single accepted answer yet, and any honest account of this story has to say that clearly. But there are several serious proposals on the table, and they are worth walking through, because each one points toward a different picture of how the early universe actually worked. The most conservative explanation, the one many astrophysicists lean toward first, is that early star formation was simply far more efficient than anyone assumed. A team led by Avishai Deckel proposed a model sometimes called feedback-free starbursts, the idea that in the earliest, densest pockets of gas, stars could form at close to maximum efficiency for a brief window before the radiation and stellar winds from those new stars had time to push back and choke off further star formation. Under normal circumstances, that feedback acts like a brake, slowing star formation down almost as soon as it starts. Deckel's model suggests that in the first few hundred million years, in unusually dense environments, that brakes simply had not kicked in yet, allowing gas to convert into stars unusually fast, for a short but critical period. If correct, this alone could explain a large share of the overmassive galaxy problem without requiring any change to the underlying physics of dark matter or gravity. A second proposal points not at star formation itself, but at the initial conditions of the universe. Standard cosmology assumes that the tiny density fluctuations left over from the Big Bang were distributed in a fairly smooth, predictable statistical pattern, something cosmologists call Gaussian. Some researchers have suggested that if there was slightly more primordial non-Gaussianity than assumed, meaning slightly more rare, extreme density spikes scattered through the early universe, those spikes would collapse into massive structures far earlier than a smooth distribution would predict. This would not require inventing new physics so much as adjusting one of the starting assumptions that feeds into every simulation. A third line of thinking looks at dark matter itself, Most simulations use what is called cold dark matter, a version where dark matter particles move slowly and clump efficiently at all scales. Some researchers have modeled alternatives, including warm dark matter, where particles move faster and suppress the smallest scale structure while potentially altering how quickly the largest structures assemble. Tweaking these assumptions can shift the timeline for when the first massive galaxies were even physically possible. And then there are the more radical proposals, the ones that get less mainstream traction but keep resurfacing because the standard explanations have not fully closed the gap. A 2023 paper by Rajendra Gupta proposed a hybrid model combining an older, largely abandoned idea called tired light with what is called covariant coupling constants, essentially suggesting that some fundamental constants of physics may have changed value over cosmic history, and that this could make the universe appear much older than the standard 13.8 billion years, potentially closer to 26 billion. It is important to be clear that this kind of model remains a minority position, and it has not displaced the standard picture. But its existence, and the fact that it gets published and debated at all, tells you something about how much pressure this handful of Webb observations has put on the field. What almost every serious astronomer agrees on, regardless of which explanation they favor, is that something about the early stages of cosmic structure formation happened faster, more efficiently, and in a more organized way than the models built before Webb ever predicted. Whether that means adjusting star formation physics, revisiting the statistics of the early universe, or something even stranger still waiting to be identified, the timeline for how quickly a young universe could build large, chemically rich, structurally organized galaxies is being pushed earlier and earlier with almost every new observing run. And this is where the story stops being just a cosmology puzzle and starts becoming directly relevant to one of the biggest open questions in science. How early in cosmic history could the universe have actually supported the ingredients for life? Every rocky planet, every carbon-based molecule, every element heavier than hydrogen and helium that makes biology chemically possible had to be forged inside stars and then scattered back into space through stellar death before any of it could become part of a new planet. That process, sometimes called chemical enrichment, was assumed to take a very long time, meaning the first generation of galaxies were expected to be almost entirely made of primordial hydrogen and helium. Essentially sterile environments incapable of building anything like Earth. But if galaxies really are forming stars faster, enriching themselves with heavier elements sooner, and settling into stable, organized disk structures earlier than the models predicted, then the window for when rocky planets could first have formed, and when the raw chemistry for life could first have existed, may need to shift earlier too. GNZ11's unexpected nitrogen enrichment is a direct example of exactly this kind of process happening ahead of schedule. If that pattern holds up across more galaxies as Webb's spectroscopic surveys continue, it suggests the universe may have crossed the threshold from sterile to potentially life-supporting sooner than almost anyone in astrobiology had assumed just a few years ago. That does not mean life existed in the early universe, and nobody serious is claiming that. What it means is that the assumptions astrobiologists use to define the so-called cosmic habitable era, the point at which enough heavy elements existed anywhere in the universe to make rocky, life-friendly worlds possible at all, may currently be set too late. Every early galaxy that turns out to be more chemically mature than expected effectively pulls the starting line of that habitable era backward, potentially by hundreds of millions of years. In a universe that is roughly 13.8 billion years old, hundreds of millions of years is a meaningful fraction of the total time available for complex chemistry and eventually complex biology to get started somewhere. Webb is still running new surveys right now, deeper spectroscopic follow-ups on more of these extreme early galaxies, searching for more examples like GNZ11 and JWST Z140, and testing whether the disk-shaped structures and the quenched dead galaxies are the exception or genuinely the norm for the early universe. Upcoming observing cycles are expected to push even further back, chasing candidates near redshift 16 and beyond, right at the theoretical edge of when the very first stars could have ignited at all. Every new data release either tightens the tension further or offers another clue toward resolving it. Nobody currently working seriously on this problem expects it to be fully settled soon. What they do expect is that the answer, whatever it turns out to be, is going to change how we think about when and how quickly a young and violent universe first became a place complex enough to eventually build something like us, and how much earlier than we imagined the raw ingredients for a habitable world may have first come together in the dark.